Hi, this is Jack from Achievers, and in this video we are going to continue with this particular paper, which is the paper from Singapore Cambridge A-Level 2022 H2 Math, and it is a paper 2. So in the previous video we have looked at section A, which is the pure math part of this particular paper, and today we are going to be looking at section B, which is all the statistics. So let's scroll to the statistics portion of the paper. So this is the pure math one that we have done. And here, section B, the statistics portion of this paper. Let's take a look at the first question, which will involve Anil and Babs. They're going to be playing this game with a fair six-sided die. The winner is supposed to be the first player to throw the same number as the other player has thrown immediately before. Okay, and in this game, according to what the question says, Anil is going to be the one who throws first. And part A, let's take a look at it. So for part A, the probability that we are supposed to find is for Anil to win the game. For Anil to win the game. So let's analyze the situation that is here, okay? So Anil is going to be playing first. Anil is going to be throwing the dice first. So for Anil to win the game, Anil needs to throw a number that is the same as what Babs has thrown in the previous one, right? So it is impossible for Anil to win during his first throw. So which means that for Anil to win, one of the possible cases will be Anil were to throw, then after that Babs throw, and then Anil throw the dice again. Okay, so it will be Anil, Babs, and Anil. So this is one possible case. Another possible case will be when Anil throw, then Babs throw. Anil throw the second time, but Anil is not winning. Then Babs throws again, and Anil throw the second time, and then Anil throws the third time, and this is when Anil will win. Let's come out with one more case first before we start to plant in the numbers. So one last case will be Anil throw, didn't win. Babs throw, didn't win. Anil throw, nope. Babs throw, nope. Anil throw, nope. Then Babs throw, no, and Anil wins during 1, 2, 3, 4, during the fourth throw. So number-wise, let's try to put in the probability and adding all the three cases together. Hopefully, it is going to get us an answer. Okay, or maybe there's even more cases. Let's try to put in some numbers first before we analyze further, okay? So for the first throw by Anil, I guess the dice can be showing any number, right? It doesn't really matter. So the first throw is going to be 1. The probability is 1, so it can be anything. For Babs, Babs is not supposed to win. So Babs will throw any number except the number that Anil has thrown during Anil's first throw. So the probability is going to be 5/6. This is the chances that Babs will not win. And for Anil to win, Anil must be throwing a number that is exactly the same as what Babs has thrown, and the chances for it to be happening will be 1/6. So here it will be 1/6 for Anil to win in the second throw. And for this case, it will be for the first throw by Anil, it will be anything. For Babs' throw, it will not be the same as Anil. For Anil's next throw, it will not be the same as Babs. And for Babs' next throw, it will be also not the same as Anil. And Anil will then win. So it will be 1/6 again. So for applying it to this, it will be this, then multiply by 5/6, 5/6, 5/6. This will be another 5/6. This will be another 5/6, and then Anil will win. And like what we were saying, this can actually go on and on and on and on. So we can actually continue this for a few more cases, in fact, all the way until infinity. Does this strike a chord with you already? Can you think of a possibility of how this can be added together? Because in our syllabus, this is most likely going to be a GP, sum of a GP to infinity. Let's try to do an analysis to see whether this is really a sum of a GP to infinity. So for what we have here, we have a 5/6 multiplied by 1/6. And for this, it is going to be 1, 2, 3. So it's going to be 5/6 to the power of 3 times 1/6. And this will be 1, 2, 3, 4, 5. It will be 5 over 6 to the power of 5 multiplied by 1 over 6, and we are continuing to add this kind of pattern all the way until infinity. And we are seeing a GP over here because the GP that we are looking at right now has the first term as this, which is a 5 over 6 multiplied by 1 over 6. And the common ratio is going to be, from this term to this term, it is going to be a multiplication of 5 over 6 to the power 2, multiplying 5 over 6 to the power 2. I'm going to be getting this. So the common ratio is 5 over 6 to the power of 2. So for this sum to infinity, the formula is a over 1 minus r, where a is this, r is going to be this. So in order for us to evaluate a, it is going to be the first term, 5 over 6 multiplied by 1 over 6 divided by 1 minus the common ratio, which is 5 over 6 to the power of 2. And this will be giving us an answer of 5 over 11. So this is part A. Let's take a look at part B. In part B, we are given that Babs wins the game. Find exactly the probability that she will win on her second throw. Okay, so this is a conditional probability question. Okay, and to write down the conditional probability, it will be the probability that Babs win, according to what the question says, Babs wins on her second throw. On her second throw, given that Babs wins the game. So Babs wins the game. Okay, let's just go for Babs will win. Okay, so this can be re-expressed as probability that Babs wins on the second throw, and Babs wins the game divided by the probability that Babs wins the game. So for Babs to win the game on her second throw and for Babs to win the game, it will be a nil, then Babs throwing the first time, then a nil not winning, and then Babs will throw and Babs will win. Okay, this will be when Babs wins on the second throw, and it will automatically also involve Babs winning the game, right? So the numerator here, it is going to be calculated as this, which is for a nil to throw, and then Babs will not be winning, so it will be 5 out of 6. Then a nil will to throw and not winning, so another 5 over 6. And then Babs will win, so it will be 1 over 6, because the chance of it happening to be the same as the previous one is just going to be 1 over 6. And I'm going to divide this by the probability that Babs win. Oh, it is Babs, so I need to put an S here. So the probability that Babs win. So the probability that Babs will win is actually pretty easy to calculate, because we already have a nil winning, right? This is the probability that a nil wins. So there are only two of them playing. So it will be either a nil who will win or Babs who will win. Okay, that is why the denominator will just be, for Babs to win, it is just 1 minus away a nil winning. So 1 minus away 5 over 11, and this will give us the answer 275 over 1296. This is for question number 6, our first question in section B, statistics. Let's take a look at the next question, question number 7. Okay, question number 7, we are going to be looking at this company that is run by an owner, a company owner, who wishes to find out about the qualification of the employees in staffing. So we are seeing this owner giving questionnaire to all the 75 employees in this department, in the staffing department, and she is going to be receiving 50 replies from 53 employees. So for these 53 employees, because they are part of the 75 employees, so these 53 employees will be taken as the sample. Okay, it belongs to 75, which will most likely be taken as the population, which means everything. So that is for part A, the answer is sample. And for part B, this owner wished to investigate the opinion, the views about the refreshment, but she doesn't have time to ask every single employee. So in order for us to be carrying out, or in order for her to carry out this investigation, what we are going to be suggesting to her is to select the same number of employees from each of the department and interviewing or doing a survey only for these few people. And because we are taking the same number from each of the department, so this will probably be giving us a more unbiased view of how a typical employee from the company is going to be looking at this refreshment facility. Okay, so that is for part B. And for part C, a pretty high weightage question over here, we are looking at this company again, where we now know that in this company there are team leaders, and there are 7 team leaders from the administration department. Let me just write down the information here. So 7 team leaders in the admin department. Okay, this is the symbol that I'm going to use, okay? So the numbers represent the team leaders. And there are 6 team leaders in the production department, and there are 4 team leaders in the marketing department, and finally we have 3 team leaders in the staffing department. According to what the question says, we are going to be forming a new team of, according to what the question says, we are going to be forming a new team of 8. Okay, this is what the question says here. So we need a new team of 8, and this team are going to be only from the leaders here, okay? So we are going to be forming this team such that they are going to consist of at least 1 team leader from each of the departments, and there must be always more administration's team leader than any of the other leaders from the other individual departments. So in order for us to work on this, we should try to think about the possible scenarios where this can happen. Okay, so let me just quote one of the possible scenarios. Let me call it case 1. So the first scenario where we are going to be having a team of 8 leaders, and there will be always more leaders from the administration department than any of the other departments. That will be when we have 1, 2, 3, 4, 5 team leaders from the administration department. Why not 6? Okay, we cannot choose 6 because according to what the question says also, there must be at least 1 team leader from each of the other departments. So from production, we will need at least 1. From marketing, we will need at least 1. And for staffing, we will need at least 1. So this is one of the possible cases where we can be choosing these 8 team leaders according to what the question says. So for this to happen, out of the 7, we will need to choose 5. Out of the 6, we will choose 1. Out of the 4, we will choose 1. And out of the 3, we will choose 1. And this gives us a 1, 5, 1, 2 number of ways. Another possibility of how this situation, how these 8 team leaders can be grouped together will be, let's reduce this by 1. A. 4 administration team leaders, and which means that we will have 4 left. And for these 4, there must be at least 1 from each. So one possible way for this to be happening will be production, then marketing, staffing. Or another possibility will be A, then it will be 1 production, 2 marketing, and 1 staffing. One last possibility, A, 1 production, 1 marketing, and 2 staffing. Okay, I should have written this a little bit closer, but anyway, these are the possible ways that when we have 4 from the administration, 4 leaders from the administrations. So for this, it is going to be 7 choose 4. Then this will be 6 choose 2. And it will be a 4 choose 1 for this, and this will be a 3 choose 1. Or this will be 7 choose 4, P. It is going to be 6 choose 1, M. It is going to be 4 choose 2, and S. It is going to be 3 choose 1. Or, again, 7 choose 4 from the administration department, 3 choose 1. 4 choose 2, and S. It is going to be 3 choose 1. Or, again, 7 choose 4 from the administration department, 3 choose 1. 4 choose 2, and S. It is going to be 3 choose 1. Or, again, 7 choose 4 from the administration department, then P, 1P, so 6 choose 1, 6 choose 1, 1M, 4 choose 1, 2 S's, 3 choose 2. And if we were to add this together, this is going to be equal to 1, 2, 6, 0, 0. And one last case, let me write it down here. Case number 3 that I'm going to be considering will be one where I want to look at A, 3 from administrations. So we will need 5 more. I'm going to have 2 from production, and 2 from marketing, and 1 from staffing. Okay, this will make sure that there will always be more administration than all the other departments, at least 1 from each of the other departments. And it will be this, or A, P, M, S. Okay, this will be another situation. Or it will be A, P, M, S. Okay, this time I have planned my spacing a little bit better. So we have this under this case where we are looking at 3 administrations in a team of 8 leaders. So it will be out of 7, we will choose 3. Out of 6, we will choose 2. Out of 4, we will choose 2. And out of 3, we will choose 1. Or 7 choose 3, 6 choose 2, 4 choose 1, 3 choose 2. Or 7 choose 3, production 6 choose 1, 4 choose 2, and 3 choose 2. And this gives us a 19530. So the total number of ways will be adding these 3 together. So it will be 1512 plus 12600 plus 19530. This will give us a total number of ways of 33642. This is question number 7. Okay, let's move on to look at the next one, question number 8. For question number 8a, we are given 2 independent random variables that follows normal distribution x and y. Let me write them down on the board here. So x is given to me as a normal distribution with a mean of p and a variance of q squared. And y is given to me as another independent normal distribution with a mean of s and a variance of t squared. Write down an expression for the distribution of the random variables ax minus by. So individually they are normal distributions when we linearly combine them together according to ax minus by, where a and b are constants, we will also be getting another normal distribution. Let me write it down here. So we are looking at ax minus by being another normal distribution. So we need the mean of this. So we need to find the expectation of ax minus by, which is going to be a expectation of x minus b expectation of y. So it's going to be AP minus BS. Okay, this is going to be here. So here AP minus BS. So we have this, and we need to fill in this space here, which is going to be meant for the variance of this. So for the variance of AX minus BY, it is going to be A square, the variance of X, minus becomes plus, B will be B square, then the variance of Y. And this is going to be equal to, here, we have a square multiplied by the variance of x, which is going to be q square, plus b square multiplied by the variance of y, which is t square. So this will be here, a square q square plus b square t square. This is for part A. Let's take a look at part B. Part B, we are going to be looking at a random variable v, which is normally distributed with a standard deviation of 2. So let me write it down first. So V here follows a normal distribution with a standard deviation of 2. So we have a 2 square here. And its mean is unknown. Okay, I'm going to just let the mean of V be mu. So what we are supposed to do is to part 1, draw a sketch to show the distribution of V, including the main features of the curve. So in part 1, what is this? This is a normal distribution. So we are expecting that this is going to be following a bell curve, the shape of a bell curve, correct? So we are expecting this, where this is going to be the V-axis. So what the question says is we are supposed to be quoting the main features of the curve, which means that we need mu to be planted here. So do we have the number mu? Of course we don't have. Okay, but the question actually gave us enough information to work out mu, because according to what the question says, the probability, let me write it down here, the probability when V is bigger than 8 is equal to the probability when V is less than 4. So what we can gather from this, looking at a normal distribution, which is going to be symmetrical about its mean, okay, is that the area that is on the left-hand side of 4 is equal to the area that is on the right-hand side of 8, because we are seeing probabilities as area under this bell curve, right? So this area and this area are the same, and since this is symmetrical in nature, this tells us that 8 and 4 and 8, okay, they are equidistant from the mean mu. So we can now calculate a value for mu, because for mu, since it's equidistant, mu is going to be equal to 8 plus 4 or 4 plus 8 divided by 2, 12 divided by 2, this is equal to 6, which means that this V, okay, is going to follow a normal distribution of 6 and 2 squares. So this number here is supposed to be 6. So this will be the feature of the normal distribution graph of the bell-shaped graph that we're going to be answering part 1 of this question. Part 2, on your sketch, can we try to shade an area that represents the probability that V is bigger than 10 and stating its value. So, this is 8, so let's say 10 is here. Okay, and we are supposed to shade, right? So the probability that V is bigger than 10 is going to be this region here on the right hand side of 10. And in order for us to do the calculation for probability that V is bigger than 10, we are going to be pressing this into our graphing calculator. And if you are using the Texas Instrument graphing calculator, then it will be pressing in normal CDF into your calculator. And the calculator will ask you for the lower limit, it is going to be 10. Upper limit, it is going to be positive infinity for this case, which we are going to press it in as E99. The mean is going to be here, 6. And the standard deviation that we're going to be planting into our calculator is square root of 2 square, 2. Pressing this into the calculator, getting an answer from this, it will be giving us a value of the probability as 0.0228. This is for part 2. And there's a part C. Okay, let's take a look at part C. Let me erase this. In part C, we have this random variable W that follows a binomial distribution. The number of trials is 8, and the probability of success for this binomial distribution is P. We are given that the mean of W, what is the mean of W? The expectation of W, right? The mean of W is equal to 1.2 times the variance of W. The mean of W is going to be 8 times P is equal to 1.2 times of the variance of W is N times P times 1 minus P. So it is going to be 8 times P times 1 minus P. This is the variance of W. So we are getting an equation that is going to be in terms of P. What am I trying to do? I'm trying to solve for P so that I can fill in the last parameter that is still unknown in this random variable W, and making use of the full known parameters subsequently, we should be able to use our calculator to find the probability that W is less than 2. So let's solve for P first. Moving everything over to one side, we have this times this is a 9.6. So we have a 9.6 P 1 minus P minus 8P is equal to 0. In fact, I'm going to divide this equation throughout by P, which will be giving us a 9.6 minus 9.6 P minus 8 is equal to 0. Why is it that we can just simply divide this entire equation by P? Because P, we already know it is the probability of success, and it shouldn't be equal to 0, or else we don't even need to discuss about the binomial distribution at all. So P is not equal to 0. That is why dividing throughout by P will give me this equation here, working out for the value of P. The exact value of P is 1 over 6, which means that W here is following a normal distribution of 8 and 1 over 6. And in order for us to find the probability that W is less than 2, with the restriction of our Texas Instrument calculator, we will try to rewrite this as W to be less than or equal to 1. So with our calculator, we are going to be pressing in binomial CDF. The calculator will be asking us for the number of trials, and that is going to be 8. The calculator will be asking us for the probability of success, and that will be 1 over 6. The calculator will be asking us for the X value, which is going to be this number here. I'll press it in a 1, letting my calculator do the rest of the part of the calculations for me. My answer for this is 0.605. This is for question number 8. Let's move on to the next question. Okay, question number 9, we are looking at this situation here where we have this board where we are going to be starting at this point here, and we're going to move upwards. Okay, according to what the question says, to move left or right, the probability is going to be equal. Okay, it is mentioned here, when leaving S, the counter is equally likely to move up to the left to junction L or to the right to junction R. So the probability to this is going to be half. The probability to this is also going to be half. And according to what the question says, at every junction after S, the counter moves up to the left with a probability of P or to the right with a probability of Q. So for example here, to the left it is going to be probability P, to the right is going to be probability Q. And the same goes for this. Anything that is after this first move, okay, it is going to be P to the left, probability P to the left, and Q to the right. And there are only these two cases because the question says that the probability P plus Q is equal to 1. So they are mutually exclusive. Let me write down this information here also. So we know for this P and Q, it is equal to 1. Okay, so from this information, we know that they are mutually exclusive. Okay, so in part A of this question, we are going to try to show that the probability that the counter arrives at point B, so it is here, at point B is equal to 2p cubed Q plus half P to the power of 4. Let's think of the possible scenarios where this is going to be happening. So let's try to imagine a possible path that the counter can take in order for the counter to get to B, okay? It can be from here to here. So it is going to be starting with a left, okay? Although this left and right are L and R, but I'm going to continue to use L and R, okay? But this is the special one, so maybe I'll just put an asterisk here. Okay, for the rest, I'm going to just use L for left, R for right. So it can be left, and then left, 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 right. So it will be left, 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 right. So this is one of the possible ways that the counter can get to B. Another possible way that the counter can get to B will be left. So it will be this special left, then left, 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 right, left. So it will be left, 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 right, left. Another one will be left, then left, right, left, left. So it will be left, then left, right, left, left. There is definitely another one which is going to be left, this special left, so L with a little asterisk there. So left, then right, left, left, left. So you'll be right, left, left, left. In fact, to get to B, there's still one more possible case, which is R. Okay, a special R. So R with an asterisk. R, then left, 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 left. So it will be L, 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 L. Okay, so these are the 1, 2, 3, 4, 5. These are the 5 possible cases where the counter can be getting to node B. Okay, so by making use of what we have just come out with now, let's try to calculate the probability. Okay, for this, it is going to be half. Okay, for the L asterisk, it is going to be half. Then after that, P, right? Because to the left is P. So it will be P to the power of 3. R towards the right is going to be Q. So Q plus, for this case, it is going to be half. Then after that, right, P square. Left is Q. Right is going to be P again. Or this will be half. Then right, it is going to be P, left is going to be Q, right, left, it is going to be Q, sorry, not Q, left, it is going to be P square. Okay, I'm really getting a little bit confused over here. So left, it is going to be P square. Or this is going to be half, then right is Q, left. So it's going to be P to the power of 3. And finally, we have this, which is going to be right. The probability is 1 over 2. Okay. Then after that, it is going to be left all the way, left. Yeah. So P to the power of 4. So this is the probability that is asked in part A. And if I were to simplify this, I will be getting a 2P to the power of 3 Q plus half P to the power of 4. And this is what the question requires us to show. So, yep, this is part A. Next, let's take a look at part B. Let me write it down here. So for part B, we are supposed to be given that, okay, this is the condition that is given to us. We are supposed to be given that John and Keith, they each play this game and their counters both arrive at B. Okay, a condition is given to us. So both their counters arrive at B. We are supposed to find in terms of P, which is this P over here. We are supposed to find in terms of P a simplified fraction for the probability that John and Keith are having their counter following exactly the same route. Okay, so they are both going to be arriving at P, and they will both arrive at P via the same route, conditional probability. The probability that, I'm going to write it down, okay? So their counters follow the same route. So both counters follow the same route. Given that both counters will be arriving at B, so both arrive at B. Okay, this is the probability that we are supposed to be calculating, and applying the formula for conditional probability, it will be the probability that both counters follow the same route and both counters arrive at B divided by the probability that both of the counters arrive at B. So which means that if both counters will be following the same route and arriving at B, this is one way that the counter will be, this is one of the routes that the counter will be arriving at B, and this should happen for both of the counters. So for this, we will go for a half P to the power 3Q times itself again, because it must happen for John, it must happen for Keith. So this square, and it is going to be the same here. So it will be a half P square QP multiplied by itself, and this again, so it will be a half PQP square multiplied by itself, and half QP cube multiplied by itself, to make sure that John and Keith, the counters are always following the same route and arriving at B at the same time. And the last one, it is going to be this half P to the power of 4 multiplying by itself divided by both counters arriving at B For a counter to arrive at B is this. So if both were to arrive at B, it is going to be having a 2p to the power of 3q plus half p to the power of 4. This is going to be multiplied to itself. It is sort of tedious for us to be simplifying this, so I'm going to leave it to you guys to do most of the simplifications, okay? And if you have had simplified it enough, you will probably be getting something that is close to this, divided by 4q plus p to the power of 2. But the question also mentioned that we are supposed to be giving our answer in terms of, according to the question, we are supposed to be giving our answers in terms of p. Okay, so we are not going to be leaving it in terms of q here. We need to do one more substitution, okay, which is this that is given to us, allow us to write q to be equal to 1 minus p. So it will be 4q, I'll re-express it as 1 minus p, then plus p squared divided by 4q, I'll replace it by 1 minus p, then plus p, the whole thing square. And with even more simplification, you will be arriving at your final expression as 4 minus 8p plus 5p squared over, this will be 4 minus 3p squared. Okay, this will be for part B. Let's move on to the very last part of this question. For the last part of this question, we are supposed to look at the probability that a counter arrives at B is the same as the probability that a counter arrives at C. And with this piece of information, we are supposed to find the value of P. We do have the probability that the counter arrives at B, and that is going to be from the answers that we have, the answer that we have derived from part A of this question. What we do not have at this moment is the probability that a counter arrives at C. And that is what we want to try to calculate for the first part. It is the probability that the counter, let me write it down, that a counter arrives at node C. Okay, so for the probability that a counter arrives at node C, this one here, let's just write down one of the possible cases first, okay? So that will be special left, okay? So it is going to be half, special left, then after that, left, left, right, right. So left, left, it will be p times p squared, right, right, it is going to be q squared. And then another possibility will be left, left, I guess, right, left, right. Right, that is another possibility. Left, left, right, left, right. Okay, so if you think about it, right, it actually shares something in common. Let me just write down for you a few cases so that we can see together, you know, what is the thing in common from getting from here all the way until C for the way that I'm reciting this. Okay, the thing that is in common that I'm trying to point out is that if I were to take left here, this special left. Okay, if I were to do this special left over here, then the subsequent ones will be left, left, right, right. So it will be left, left, right, right. Or it will be left, right, left, right, left. That means it will be left, right, left. Oh, hang on. It will be left, then after that, left, right, left, right. Sorry, I said wrongly. It will be left, right, left, right. Or if I were to, I mean, this is if I were to be starting with this special left over here, okay? So another possibility will be special left. So let me write down this special left. It will be special left, then right, left, left, right. Right, left, left, right. So it will be a right, left, left, right. So what we can see here, right, is that it always will have a LLRR. Okay, it's just different ways of them being arranged. Right, it is always going to be LLRR. So instead of me writing down a probability for this, plus a probability for this, plus a probability for this, what we can see is that it is an arrangement of these four letters, LLRR. So if we are able to see this, we are then able to do the calculations even faster, even more efficiently. That means for one of the probability, for one of the number of ways that it can, so the probabilities, it is probability. So for one of the probabilities, it is going to be P times Q times Q. This will also be P times Q times Q. This will also be P times Q times Q. So all the probabilities are the same. And the number of times this will happen is the arrangement, the number of ways that LLRR can be arranged. So we have 4 letters over here, and we are going to arrange all the 4 letters. That will be 4 factorial. 2 of the letters are identical, so I divide by 2 factorial. Another 2 are also identical, so I divide by another 2 factorial. This will make it way easier for us to be doing the arrangement. Let's see whether we can apply to if we were to be moving this way instead. Okay, so let's take a look at another possibility. So this other possibility is when we are moving right first. Okay, the special R. Let's see how we will be able to get to C. Okay, so with this special R, one of the possible ways will be L, 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 R. So let's write L, 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 R. And another way is starting with this first R. Then another way will be L, R, L, L. So L, R, L, L. We are seeing something that is similar to this happening, right? 3 L's, 1 R. 3 L's, 1 R. Let's code another possible scenario so that we can see the pattern, okay? So R, okay, then after that it will be L, R, L, L. How about that? Oh, I've already done L, L, L. So how about L, L, R, L? Okay, so it will be L, L, R, L. So this once again shows me that every time when I get from S via this R to C, right, there will always be 3 L's and 1 R. So the probability will be, for the special R, it is going to be half. 3 L's and 1 R, it is going to be P to the power of 3 and a single Q. P to the power of 3 and a single Q. And we are going to be arranging these 4 letters just like what we have done here. So it is going to be a 4 factorial. 3 of the letters are the same. So I will divide this by 3 factorial. This is the probability that we are going to be getting in order for a counter to be arriving at Q. So simplifying this, we will be getting a 3p square q square plus this will be a 2p to the power 3q. And according to what the question says, this probability is going to be the same as the probability that the counter arrives at B. So these 2 probabilities are the same. So we will be letting the answer that we have gotten from part A, which is 2p to the power 3q plus half p to the power of 4 to be equal to this probability, 3p to the power 2, q to the power 2 plus 2p to the power of 3q. And again, I'm going to leave it to you guys to continue simplifying this, which you will then arrive at something that is similar to my equation over here. 4pq plus p squared, this is 6q squared plus 4pq. And from here, according to what the question wants, we are supposed to try to solve for p, right? So for this equation, we will once again replace all the q's by 1 minus p. So it is going to be 4p, this q, I'll replace it by 1 minus p plus p squared is equal to 6. This I'll replace it by 1 minus p. Then 4p, this q, I will replace it by 1 minus p. So now we have an equation that is in terms of p. Simplifying this even further, we have a 5p squared minus 12p plus 6 is equal to 0. Pressing this into our calculator to solve for p, we will have p to be equal to 0.710 or p to be equal to 1.69. We are going to be rejecting this p. Why is that so? Because p is a probability. Okay, and all probabilities are going to be between 0 to 1. So we are rejecting this because p is supposed to be less than 1. So this is question number 9. Let's take a look at the next question, which is a correlation linear regression question. Okay, in question number 10, we are looking at Ariana investigating the price of used car in pounds sterling versus the distance that the car has been driven in miles. So we are looking at D representing the distance and P representing the pound. And this is the scatter diagram that is given to us, that is already plotted against the table that is tabulating for us D versus P. And the next part of the question, or the first part of this question, is telling us, is asking us what kind of conclusion should Adriana reach about the relationship between D and P. We're also given another piece of information here, which is the product moment correlation coefficient between D and P is negative 0.78. So a negative 0.78 is not exactly the strongest kind of product moment correlation coefficient that we are looking for to conclude whether the relationship is to conclude that the relationship between the two variables, right, is like super linear. So based on negative 0.7, what I think we can still manage to say about the linearity of the two variables will be something that is like, they are being moderately strong, not exactly the strongest, but they are also sharing a negative linear correlation. And then looking at the scatter diagram that is given to us here, right, it is actually pretty obvious that the scatter diagram is showing us a curvilinear relationship. That is why the conclusion that, based on the information that is given, the conclusion that Adriana should be concluding will be the conclusion that she will be concluding. But anyway, Adriana's conclusion should be that the relationship between D and P, right, is something that is a bit more non-linear. Okay, that is going to be for part A. Part B, we are supposed to explain whether the product moment correlation coefficient will differ if Adriana were to be converting the distance, which is currently in miles, to kilometers. And the conversion is given to us here. 1 mile is 1.6 km. And the price to Singapore dollars, the current price that is given to us for P is in pounds sterling. Okay, so the conversion rate is also given to us as this 1.7, which means that we are going to be multiplying D and P by a constant. Okay, and these are considered as linear transformations. And we have learned before, linear transformation is not going to cause any changes to the value of the product moment correlation coefficient. So that will be how I will be answering part B. And then next, moving on, Adriana checks the original information and she realized that this particular set of data, D5055, P is 22500, which is actually this last set of data here. D is 5055, P is 22500. According to what the question says here, she realized that for this particular set of reading, it is actually meant for a special version of the car with a bigger engine and with many extra features. But what we are trying to do here, right, in order for us to be comparing them, gauging the relationship between them, we want to make sure that the cars that we are analyzing, that we are comparing, they are of the same model and they are of the same make. Okay, they must be as similar to each other as possible. That is why this special version, which according to the question, we already know it is going to have special bigger engines and many extra features, it shouldn't be used together with the rest of the other data to do our analysis here. So this is going to be for part C. And that is, I guess, why the rest of this question should not include the data for this special car. Okay, so let me just remove this and before we proceed to part D. So moving on, we are going to be removing this set of data from our table because that is meant for the special car, and that is what the question says here. Okay, and the next thing that we're going to try to do is to come out with a scatter diagram for P against 100,000 D. So I will be planting this into my calculator, and from my calculator, this is the table that I've gotten. And for what I have there, I have let L1 be D, and I have let L2 be P, and for L3, I have generated it myself. L3 is going to be representing this 100,000 over D. So with my calculator, I will plot a scatter diagram, and the scatter diagram looks like this, which I have replicated here on the board here, right here. So, and from this, we are supposed to draw a line of best fit. Okay, it is the best fit line by eye. So it is just a rough estimate of the best fit line that I'm drawing here. So this is for part D. Show on the scatter diagram in part D the distances which are used in drawing the least squares line of P on 100,000 D. So the question says this: P on 100,000 over D. So this piece of information that is given to us by the question. Okay, I should show the question here. Okay, so it is this part of the question. So we are looking at this P on 100,000 over D. So the moment when the question mentioned this P on 100,000 D, the question is suggesting that P over here is the dependent data and this is going to be the independent data. Okay, so the error is going to be lying in P, and what the question is trying to talk about as in terms of this distance. Okay, this distance here, this distance, if we were to try to indicate on our scatter diagram, this distance is the error that is on P. Okay, because P is the dependent data. P is the one that is dependent on the experiment. So P is here, which means that the error that we are going to be talking about, right, will be this distance here. Let me just indicate in red. Okay, so it'll be like this distance here, this distance here, this distance, these vertical distances here. We're a little bit tiny, but that is the error that P makes. Okay, these crosses here are the experimental points. These are the data that have been obtained from the survey, and this line here will be representing the theoretical estimation. Okay, the theoretical values of P. So we are taking the experimental and the theoretical values. The difference between this will be the distance that the question is mentioning. So this will help. I mean, with this idea, it is going to help us to explain why these distances are supposed to be squared and why this is referred to as the method of least squares. The reason is because when we try to find these distances, we tend to take the value of the P coordinates of the point, the experimental point, and the P coordinate that is on the least square lines. We find the difference of it. So if you were to find the difference between them, depending on which one is bigger, sometimes the experimental P may be bigger than the theoretical P. Sometimes the experimental P may be less than the theoretical P, which means that if you were to find the differences, our values can be either negative, 0, or positive. So what we want to do in order for us to generate the least square lines, or using this method of least squares, is to try to sum all these distances together. But since sometimes they can be positive, sometimes they can be negative, sometimes they can be 0. So one good way of summing them together is by squaring them. Okay, that is what we can make use of to try to explain about why is it that we are going to be squaring the distances. And in order for us to generate the least square lines, the method is square the distances, and we will try to sum up all these squared distances, and then we try to make sure that when this line is being adjusted to become the best fit line, the sum of the squares are going to be the least. Okay, that is how this method of least square is going to be conducted. That is going to be for part E. Let's move on and take a look at part F, where we are going to be generating the least square regression line as a form of equation. Okay, so now in part F, we are supposed to come out with the least square regression line of P on 100,000 for part F. So we will plug this set of information that we have obtained into the calculator again to generate the linear regression line together with the product moment correlation coefficient. And this is what I've gotten, which means that the least square regression line will be something that is like P is equal to, using the coefficients that is provided for us by the calculator, it is going to be 505.73 of 100,000 over D, then plus 9398.5 So P is going to be the simplified version, 506,000,000. So 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5. That's correct. So this over D plus 9400 to 3 significant figures. And again, from this same part of my calculator, we can write down the product moment correlation coefficient, and according to what that is on my calculator, it is 0.987. Actually, it is a pretty good product moment correlation coefficient as compared to what we were looking at just now, a negative 0.78. And then the question went on to ask in part G, we are supposed to use the equation, this equation, to estimate the price of a car of this make and model that has traveled 5055 miles. So we are talking about us trying to estimate the value of P for the D that is given. So when D is equal to 5055, isn't 5055 a little bit familiar? It is actually this, right? The one that we have actually crossed out. So when D is 5055, let's look at the price. The price is going to be making use of this, but we're going to use more significant figure. Okay, maybe let's make use of this. Okay, this is all rounded off to 3 significant figures. So making use of this, we are looking at 505.73, 100,000 over D, which is 5055, then plus 9398.5. And we're going to get the price to be equal to 19400. The question went on to ask us to explain whether we will be expecting this estimate to be reliable. First of all, we are already looking at a value of D that is outside the data range. Okay, the data range of this particular set of D is for D to be between, let me just write it down. Looking at all these values here, right, the smallest possible D is 8954. The largest possible one that is according to the data is actually this one here. So it's 45452. So D that is being asked, that is being mentioned by the question for us to do the estimation, this value is actually a value that is not within the data range. It is pretty small. Okay, that is why, because it is not within the data range, we will be expecting this estimation here to be unreliable. Okay, that's how we will be answering part G. Okay, the estimation is unreliable. Let's look at one more question. It is our last question. It is a question that is a mixture of normal distribution and hypothesis testing. Okay, question number 11. We are given the normal distributions of the time that Zhou and Tan are going to be swimming this 100 meters in freestyle. Okay, so we are going to be letting X be the time that is going to be taken by Zhou, and we are going to let Y be the time that is taken by Tan. And according to the question, X here will follow a normal distribution with a mean of 80 and a variance of 2 square. And also according to the question for Tan, the timing is going to follow a normal distribution with a mean of 79 and a variance of 3 square. And in part A, we are supposed to find the probability that Zhou wins a randomly chosen race. So we are talking about them competing to be faster, right? So for Zhou to be winning, that means the time spent must be shorter than the time spent by Tan. So we are going to be trying to calculate for the probability where X is supposed to be less than Y in order for Zhou to spend less time than Tan, so Zhou will win the race. So in order for us to be calculating this, we will be bringing everything over to the left hand side, or you can also do it for the right hand side. I'm going to go for bringing everything over to the left hand side. So we are trying to calculate this by calculating for the probability that X minus Y is less than 0. So we do need a distribution for X minus Y in order for us to be pressing it into the calculator. Let's try to find the distribution for X minus Y, which will be a linear combination of the two independent normal distributions. So it is still going to continue to be a normal distribution. We need the mean and we need the variance in order for us to press into the calculator. So for the mean, the expectation of X minus Y, this is going to be the expectation of X minus away the expectation of y. So it is going to be equal to 80 minus 79. This is going to be 1. We will need the variance of x minus y, which is going to be the variance of x plus the variance of y. So the variance of x, this is 2 square, plus the variance of y, this is 3 square. This is 13, so here we have a 13. Pressing this into the calculator using normal CDF. If you are using the Texas Instrument calculator, the probability here is going to be 0.391. This is for part A. And then according to the question for Joe is going to be going through this exercising regime, okay? So for this way that he's exercising for the sample that he has collected, we are looking at n to be equal to 30, so it is recorded for a sample of 30. The sum of the 30 samples is given to us. The sum of the square of the 30 samples is also given to us. This is the time that is taken in seconds. Part B, we are supposed to now calculate for the unbiased estimate for the population mean. The unbiased estimate for the population mean, it can be calculated. So the unbiased estimate can be calculated by the sample mean. So that is going to be summation of x over n, and this will be summation of x is given to us as 2376.3 over n. N is equal to 30 over here. So this is going to be equal to 79.21. And for the population variance, the unbiased estimate is going to be calculated as s square, and it is going to be 1 over n minus 1 summation of x square minus summation of x, the whole thing squared divided by n. Plugging in the values, it is going to be n, which is 30, and summation of x square, let's see, from the question, summation of x square is 188653.7 minus away summation of x, which is 2376.3, so this square divided by n, which is 30, and this will give us the unbiased estimate of the population variance, and that is 14.7. Let's move on. Let's take a look at part C. In part C, we are going to be carrying out a hypothesis test at 5% level of significance to test if Joe's time has been reduced. So I'm going to be letting mu be Joe's mean time for a typical randomly chosen swim, which means that for my hypothesis, H0 is when mu is going to be equal to the originally thought of population mean, and we are going to be testing whether this mean has been reduced. So it is going to be less than 80 for the alternative hypothesis. The sample size, as mentioned by the question, is 30, and from the previous part B, we have come up with the sample mean, and the sample mean x bar here is 79.21. This is from part B. So for the test statistics that we are going to be working on, let me just write it down. The test statistics. The test statistics that we're going to be working on is going to be meant for x bar, is one that follows a normal distribution with the population mean being given here, and what that is here is going to be the population mean divided by the sample size. What is the population mean? The population mean has also been given to us by the question. It is the the population variance is going to be here. The population variance is given to us by the question in the very first part. That is going to be 2 square. So here is going to be 2 square population variance divided by the sample size. So divided by 30. This is going to be our test statistics. We are going to be pressing this set of information into the calculator, and from our calculator, we are going to be retrieving the p-value. Let me write down the p-value that we should have gotten from the calculator using this set of information. The p-value is 0.015251. And now we compare this to 0.05, which is 5% level of significance. We do realize that this p-value that we are looking at here is less than 0.05. So this implies that there is sufficient evidence, right? Sufficient evidence that Joe's times has been reduced. Let me write down my conclusion. So therefore, there is sufficient evidence that Joe's swim time have been reduced at this 5% level of significance. Okay, let's take a look at the next part of the question. Okay, so in this last part, we are looking at Tan, who is going to be carrying out another hypothesis test, and that is when he was already away for 2 years, and then 1 year later, he's going to be carrying out the test based on this new diet that he's probably taking. Part D, explain whether Tan should be using a 1 or 2 tail test. According to what the question says, after Tan decided to do the test, he's trying to do the test after 1 year. When Tan decides to do the test, he is trying to do the test to check whether the mean time has changed. Okay, so we are looking at whether the time has increased or decreased. Because it is timing that has changed, that means for mu, it is going to be not equal to the original time. So we are talking about change, which means that we are going to be picking a two-tailed test. And in order for Tan to be conducting this test, the assumptions that we can make in order for us to answer part E is that after a while, things may have changed, but we are still going to assume that for Tan's swim time, it is still going to be following a normal distribution. And because we are looking at 6 different samples, so in order for us to be putting them together, we are going to also assume that for the swim times, they are always going to be independent of one another. Okay, this is going to be for part E.